Welcome to another video of CS360, and this time we will cover the recursion theorem. Okay, so the recursion theorem is a kind of a powerful theorem in computability theory, and it basically says that a Turing machine, in a sense, can be assumed to have access to its own source code. So it's kind of a weird thing to say, like, why can a general machine be assumed to just have its source code lying around that it can talk about? But we'll see that this theorem more or less guarantees this in a formal way. So, okay, so let's state what we mean by this theorem. So the theorem is basically saying that if M is any program, any computation that depends on both some string W and some code of another Turing machine. So if you have any computation that depends on the code of some machine and W, where W is anything else. Okay, so it depends on the code of the machine and potentially on anything else. Any such computation M, then there's also another Turing machine Q, such that when you give QW, then Q runs M of WQ. Okay, so basically, what happened here is that this machine Q runs exactly the computation M that we described there. It runs exactly that on its own source code. Okay, so for any computation you might describe that has to do with the source code and has to do with anything else, you can create a program that takes input to that something else and runs that computation on its own source code. Okay, so this is just a general way of saying for any computation you can describe, there is a Turing machine that runs that computation on its own source code. Okay, so this is just this is the formal statement of the recursion theorem. I think in the notes the order of W and this input code were flipped, but of course that doesn't matter. Just a notational convenience thing. Okay, so right, so let's first talk about how we might use the recursion theorem. It can be used to get various kind of paradoxes and therefore contradictions. So you can use it in various proofs by contradiction. One classic way of doing this is that to prove that the halting problem is undecidable. So the way we do it is we say suppose that Turing machine P decided the halting problem, this HTM thing. Okay, so then we will describe a Turing machine Q. So then, so what will Q do? So Q on input W, it will basically gets its own source code. From the recursion theorem. And then Q runs then Q runs P on QW. Okay, so this is asking P whether Q is going to halt at W. And then basically if P says halt, like if P accepts basically, then loop. And then if P says loop, then halt. Okay, so we just do the opposite. Okay, so basically we run the program P on our own source code Q and the same input W that we got. And then if P accepts, basically, if P predicts that this program Q will halt when I run W, then enter an infinite loop. Just go like, while true or something, just enter an infinite loop here. On the other hand, if P says that this computation, that Q will never halt when run on W, then immediately halt. Okay, so this is the same kind of paradox. So now, of course, when you run Q on something, then P must get the answer wrong, right? Like if P says that it will halt, then of course Q loops, and if P says that it loops, then it halts. So P of course gets the answer wrong here, which is contradicts the assumption that Q decides HTM. Okay, so this is kind of the same version of the proof that the halting problem is undecidable. We sort of, by this definition, we kind of immediately get a contradiction here. And so the only question is, why was this step, basically what was the first step allowed? How did we get our own source code Q? Why was that legal? Generally when you have a Turing machine, where did it get access to its own description from? It's not clear that that's a legal assumption. And so that's where the recursion theorem comes in. So the recursion theorem basically says, okay, maybe we don't have the source code Q. So let's instead call this, N. Oops. Okay, and we will define a computation. So we will define a computation. So let's not call this Q anymore. Let's call this M. And what M does is M, when you give it a source code, when you give it a source code N and a string W, M does the following. M does exactly what we described, okay, on the source code N instead of Q. So we just removed all mentions of Q and we replace it with the Turing machine now takes the source code N. So this will also be N here. So the Turing machine now takes the source code N as input. So of course it can do this, of course. So the whole first line is basically gone now. And of course it can run P of N comma W. That was the input. So of course M can do this, but that won't give us a contradiction. If we just say that M is going to run P and then do the opposite of what P said, that's fine. It just makes M do the opposite of what N did. Okay, so here, the way we defined M loops on this input if N halts on W, and M halts on this input if N loops on W. Okay, so that's fine. If we had access to P, then of course we can define such M, which does the opposite of what N does on W. Okay, so that's no mystery. But now we apply the recursion theorem to M. And what the recursion theorem says is it says there will be a single machine Q, which takes in just one input W, and then it runs M on its own source code Q. So what Q does on W is the same as what M does on Q. So now we get M of, what M does on Q is, of course, it puts in Q's for each N. So what M does on input Q comma W is, it does the opposite of what Q does on W. So now we got back our original program. Okay, so basically every time this trick is pretty general. So every time you have a line that says get own source code from the recursion theorem, that line is basically legal because you can sort of go back and implement this line in two steps. First, describe a machine M, which take this source code as input, and then apply the recursion theorem to that machine M, and you will get a machine Q that really does run the rest of the computation on its own source code. Okay, so essentially this is why the first line is legal. The recursion theorem basically guarantees it. Okay, and from the recursion theorem, we immediately prove things like the halting problem is undecidable. There was a problem on one of the quizzes. It was asking, if M is a Turing machine, is there a TMQ such that what m does on q, what n does on input q is equal to what q does on input m. Okay, so does this always exist? And but by equals here, I mean if one loops, the other loops. If one accepts, the other accepts. If one rejects, the other accepts. So they do the exact same thing. Okay, so is it true that for all Turing machines M, there's a machine Q that has this property? Okay, that was the question on one of the quizzes. And the answer was yes. And the reason is that so we want to define such a Q. Okay, so Q will take as input the description of a Turing machine, and what we want Q to do is first get its own source code Q from Recursion Theorem. Okay, and then run n on Q. So, and by that it means simulate this input Turing machine when run on Q. Okay, and now when you run this program, when you run it on input m, so you run Q on input m, then you can see that what this machine does is it simulates, it just simulates m run on input Q. Okay, that's just by definition what it does. So they do the same thing. So that's why that quiz question had the answer yes. It basically follows from the recursion theorem in this way. So the recursion theorem can give you all sorts of neat results. So this is kind of a weird thing that, for every Turing machine M, there is a Turing machine Q such that M run on the description of Q it does the same thing as Q when run on the description of M. Pretty bizarre thing to claim, but it's true from the recursion theorem. Okay, so how do we prove the recursion theorem? So how do we prove the recursion theorem? So remember, we had M which runs on like, this thing. And what we want is Q. And we want Q of W to run M of Q W. Okay, so that's what we want. Okay, so right, so how do we define this program Q? And so so the way we had it in the notes, basically the machine Q will basically be these composition of three machines. Basically, we have a Turing machine P, and then a machine R and a machine M. Okay, so basically Q is going to be basically equal to this thing. And so first of all, so there's a bit of some notational issues here. So first of all, when I put two Turing machines next to each other, when we put Turing machines like R and M, if I put them just next to each other, this is basically saying that we will run R first, okay, and R will change the tape in some way, and then after R is done, we will run M. Okay, so we get one machine. So this R concat M, in a sense, or R next to M, gives us a new Turing machine, which basically simulates it runs the first Turing machine, and when the first Turing machine is done, it transitions to running the second Turing machine. Okay, on the same tape, on the same tape contents. Okay, so if R changes the tape contents in one way, then M runs on the changed tape. Okay, so first we run R, then we run M. And so here we have a concatenation of three Turing machines, P with this subscript R and M. And that means first we will run P, then we'll run R, then we'll run M. Okay, so this is one thing to understand here. So we first run P, then R, then M. Okay, so what does the machine P do? So the machine P, the machine P with any subscript S where S is any string, And when it runs on a tape that has W written on it, so when it runs on input W, what it does is it prints the string S comma W on tape. So what it does is it just prints S before W. Okay, so we had here we had W written on the tape, right? To take input W means W was written on the tape when we started. Okay, and here S is hard coded into the description of P. So it's hard coded into the code of the machine, essentially, into the code of the program. And all P of S does is it prints S. So, okay, so this is pretty simple to describe machine. So we won't go to the details of how it's printing S, but it's pretty simple. I mean, for a Turing machine to print something out, you just have one state for each character of S and you just go one by one and print them. You have to do it before W. So, okay, so you have to be a little bit careful that you're printing it before W and not after. And, you want this tuple, so you want some separator symbol. And if you don't have a separator symbol, you may want to change the alphabet slightly in some kind of fixed encoding. Okay, but that's all boring implementation details. We can surely print the string S before we print the string W and put some separator in between using a Turing machine. Okay, so this is what the Turing machine PS does when it takes input W. Okay, so now that explains what P is doing, and P is doing this. The string it's doing it to is the description of the machine RM. Okay, so RM is one machine which runs R, then runs M, and P is doing this to the description of that machine, to the encoding of that machine as a string. Okay. So what is the machine R? So we know what the machine M is, right? Yeah, M is this machine. M is the machine we started with that we want to convert it to Q. We want to kind of have Q run M on itself, right? M is what we want Q to do to itself. So we know what M is. Okay, but what is R here? So R is a kind of interesting machine. R basically takes as input something that looks like this. It expects to take as input a machine and then a string. Okay, and what it wants to output is like this kind of thing. Okay, so here's what R is trying to do. R looks at the input tape. We don't really care what it does if the input is not formatted like this, but we assume that the input is formatted as two strings separated by a separator. And then the first string has to be an encoding of some machine. Okay, so if the input doesn't look like this, it doesn't really matter what R does. But if the input does look like this, here's what R is going to do. R is going to ignore the second part of the input. It's going to leave it alone. That's just going to stay there. Okay, but for the first part, this machine N, R is going to do something a bit weird to it. Okay, so first of all, R is going to define this Turing machine P, which prints out the description of N. Okay, this is this machine that we talked about earlier. So N, the description of N is just a string. So R can of course talk about construct to this machine that prints the string N. Okay, and then what R is going to do is R is going to connect that Turing machine to the actual Turing machine N and kind of get a combined Turing machine, which first runs P sub N and then runs N. So this is the combined machine, P sub N concat N. It's one Turing machine, which combines them both. And what R is going to do is R is going to write down the description of that machine. Okay, so again, R starts with the description of the machine N. Okay, and what R does is first it comes up with the description of a machine that prints out this description of N. Okay, and then after it prints out the description of N, R connects that to the description of N itself and gets one description of a machine which first runs P sub N and then runs N. And R puts that whole description of this complicated machine before W. It ignores the second part of the input, which is W. Okay, so this is what R does. R only does this weird, bizarre thing if the input is formatted like this. And if so, this is what it does. It maps N comma W to PNN comma W. Fine. Okay. So that's it. So this is so now this is the machine here, Q. It's P. We first takes as input W, first runs this P on it, then runs R on the result, then runs M on the result of that. Okay, so let's see what that does. Okay, so what does it do to a string W? Okay, so let's work over here on the left here. So what does this do to W? So the first thing that happens is we run this P on it. Okay, and what we said is that P sub S on W prints this pair. So what happens when we run on W is we run P on RM, and what we get is well, the pair RM, or sorry, no comma here, R concat M W. Okay, that's just by the definition of P. That's what P does when run on W. Okay, and then we're like over here. We already run P. So the next thing we do, we're like here. So the next thing we do is run R. Okay, so we run R, and this is what's written on the tape right now. So we run R, and what does R do? Well, R checks if the input looks like this, and the input does look like this, right? The input looks like a description of machine, comma W. So what R does is it prints out this instead. So so what we get on the tape after R runs is we get this pair. So we get P and then subscript RM. Okay, and then we get RM, the description of all that, comma W. Okay, so and now we're here. So now we already run R, and the next thing we do is run M. So we run M on that. Okay, and then that's it. That's the end of the program. So what Q does, this is what Q does on W. So this is Q on W does this. Okay, so what we conclude is basically let's start a new page here. So what we conclude is that Q on W runs M on okay, so what was it? It was P RM R M W. That's what we concluded. Okay, but note that Q was P R M R M. This is what we defined Q as, right? That's how that was our definition of Q. That's the whole thing we started with. So what happened here is that so basically Q of W is running M on Q W. Whoops, like this. So what happens is M is really running, so QW really runs M on its own source code, MW. Okay, and so this is the bizarre thing that we kind of printed Q's own source code on the tape before W, and then we run M. Because this is what we did. We had this Q was sort of like a Quine, a machine that prints its own source code. And what it did is on input W, what Q did is it printed its own source code first before the input W onto the tape, and then it ran M. Okay, so it did the Quineline thing of printing its own source code. And how did we implement this? We implemented it by basically this P RM kind of trick. Okay, so we had a printer sub function that just prints a string. So that was the printer procedure P. And then we also had this weird R procedure that takes in basically the description of a machine and translates into, a thing that runs the printer that generates that description and then runs the machine itself. Okay, so R does that complicated operation. So you can say maybe R is the most difficult part to actually implement here, but it's still not that difficult, right? It's if you think about what R is actually doing, there's nothing. R doesn't need access to its own source code for input. For instance, R is only running something on a source code that it's given, and it's running something not that complicated. So it should be pretty clear that this is well defined, that we can actually implement P and R, the components that we need here. Okay, and that's it. So that's the recursion theorem. It's a very useful theorem, and it's good to try to get familiar with it. It sort of can prove almost any undecidability or any uncomputability problem or undecidability problem that you need proven. Often the recursion theorem has a way of doing it. So it's a very powerful result. All right.